I just finished doing a live real-time debug of OBS. The recording has started, I think. We'll find out after the fact. And I'm going to go ahead and kick things off. Feel free to grab your burritos, pop a squat somewhere. No rush. You can keep eating. You won't need to take notes. Your mind will be too blown for that anyways. All right, here I go. Hello, everybody, and welcome to How to Attack Networks. You may be shocked to learn this, but in this workshop, we will be attacking networks. Yes. Over the course of the next 122 slides, I will render CSC 123 a complete waste of your time, if it isn't already. The check-in code is attack networks. I accidentally leaked it on Discord with my selfie earlier. Whoops. You can redeem this code at members.acmucsd.com in exchange for membership points, which can then be redeemed for ACM-branded swag at the ACM-branded store. Something I wasn't sure was going to happen before I graduated. But here we are. Thank you, Steven! I'm told the Aaron plushie will be going on sale soon. Yeah, start saving up now. All right. So this workshop and its contents are brought to you by ACM Cyber at UC San Diego. ACM Cyber is a special interest community of the largest technology organization at UC San Diego, the Association for Computing Machinery at UC San Diego. ACM Cyber also happens to have been awarded UCSD's Org of the Year 1 year ago. And this year they canceled the award, so that basically means we've been UCSD's number org 2 years in a row. We aim to provide member first, and I'll skip all this. By the way, our largest event of the year is San Diego CTF. That stands for Capture the Flag. This competition is a 24-hour Jeopardy-style hacking game. Not like literally Jeopardy, like I'm not going to ask you questions. It's just there's categories. That's all that means. It will be taking place on May 6th in this very room at this very time, so show up, although it's a Friday. So basically, you can just stay in your seats after this workshop, and you'll be there. This is our second annual occurrence of the largest CS competition on campus, and we encourage participation. I just realized my music's still going. Sorry about that. It was kind of calming, though. Anyways, we encourage participation from all ACM communities, from all of UCSD, and from teams across the entire world. You can visit our website, sdc.tf, for more information and to pre-register, which amounts to joining a Discord server, for more details as we draw closer to the main event. All right, shill over. Hi, everybody. This is me. My name is Aaron. I've been a notorious serial network attacker for many years now. I'm completely unqualified to teach this workshop because I'm not a computer science student. UCSD agreed that I'm clearly not good enough and I couldn't enroll in their class if I wanted to. I used to be president of ACM Cyber, but now I just manage SDCTF, which I am resisting the urge to plug for a second time. Ah! Let's go back. There it is. For a second time, my greatest ambition is that I would like to graduate in exactly 1,284 hours from now on June 11th, and perhaps make some money at some point. My fun fact is that this is the first in-person workshop I've given in 2 years, and it's also my last. So let's make it a good one. Here's our agenda. Since none of you know, I'm going to tell you what networking is. Then we're going to do some networking models. And then that third one, you'll see. The first one, what is networking? Wonderful. Glad you asked. Originally, I had a demo here where I show you what Wireshark is, but I hate Wireshark. Raise your hand if you've used Wireshark before. All right, keep it up if you hate Wireshark. Yeah, that's what I thought. That's what I thought. So like I was going to give a little thing where you open up, like all of you on your computers, open up Wireshark, but I think there's a lot of people here that don't have it. UCSD Wi-Fi is slow as it is. Let's just skip this part. I'm going to talk for a long time. But feel free to, in the background, if you want, try out Wireshark. You can literally just install it, go Google it, install it, run it on your computer, and sniff local traffic. You won't get anything but your own traffic, but Windows is pretty noisy, so you'll still get a lot. And you'll see something like this, which is a list of all the network traffic coming in and out. Each row on this is like a packet. You've got columns indicating data about it. It's a network analysis tool. But instead, I'm just going to talk about it. But if you should so please and you're bored, feel free to set this up and try it out in the background. Congrats, you passed the first section of this presentation. We're already a third of the way through. Now we're moving on to networking models. I'm just going to sum it up in one slide, really. This is basically what network traffic looks like. Does anyone ever get a package from Amazon that looks like this? It's like, it's always one extreme. It's either like a glass ornament in a 3-foot box and no packing material, or it's like this picture and you just ordered like a pair of earbuds and they're in there. You know, it's never something reasonable. This is basically what you send every time your computer sends a packet. It's not just one of these either. It's thousands, if not tens of thousands of these per minute. And it's not just your computer either. It's everyone's computer. Everyone is sending these all the time, and they're all individually very complex. So how do computers tell them apart and make sure every packet gets to its location in order and all that other stuff? Well, this is where the networking protocols come in. There are 4 layers, or 4 boxes, that your information generally comes in whenever it's beamed over the internet. First, the link layer, which contains the internet layer, which contains the transport layer, which then finally contains the application layer. Each layer has different responsibilities, and we will get into each of them. But sometimes, we don't even need all 4, you know? Sometimes 2 or 3 will suffice for talking to a computer on your local network or something like that. And each layer can also be swapped out in exchange for a different protocol. These are designed so that they're interoperable. They're supposed to be anyways. Meaning that there are many different combinations of protocols and that are often used together to make your computer work. I'm not going to go over all of them. We don't have the rest of the school year. But what I just showed you is the TCP IP model of looking at the internet. It's a way of looking at computer networking as 4 layers, but there's another much older model of networking that predates the internet called the OSI model. It was created in the 1970s. Oh, this is a fun one. Did you know the OSI model was created by the International Organization for Standardization, making it the OSI model made by the ISO? Who here has heard of the OSI model? Yeah, there's a few of you. Do they teach it in like 123? They do? If you're ever in an interview and get asked about the OSI model, just tell them they should be using TCP IP instead. Literally, I was in a job interview and they asked me, and I was like, well, I think I really only studied the TCP IP model, and they're like, you're good. We don't need to even hear it. We're good. As long as you know that, you're good. So, okay, to help you understand, that's all I'm going to say, by the way. Whatever. OSI model is like 7 layers. It doesn't really match what happened, like the way most internet traffic works. So that's why TCP IP is better. To help you understand how these all fit together, I'm going to show you a motivating example, a single packet that we can take apart into its 4 layers. Are you ready? Here it is. Anyone know what this says? Let's see here. OK, so yeah. Damn it. You're right. Isn't it beautiful? I mean, think about it. Isn't that all computers are, 1s and 0s? Right? This is a real network request that my computer sent when I visited a website. I didn't just make up those 1s and 0s. The 3,128 bits on your screen right now is what my computer sent over somewhere to request a web page. So what I want to do is break this into 4 layers and understand and assign meaning to every single one of these bits. But maybe we could, I don't know, compact it a little bit first. So let's visualize this in a different way. Let's break these up into their 8-bit chunks, right? Each of these clusters is a byte. And we're going to use monospace because that's the only real way to look at binary. And then, we're going to convert it into hex. There we go. It's a lot simpler. This is just the same exact information as before. It just takes up less space because we can use more characters. And then next up, we are going to align it into 16 column rows. We are going to assign line numbers. We're going to adjust the font and spacing. Got to make it look nice. Doesn't need to be readable. Let's see here. Oh, and lastly, we give it that little indentation. So you've got the 4-byte clusters and the 8-byte clusters. It's just easier to parse. It's customary. OK, and there we have it. This is the whole packet. It looks far less daunting. We can break this up. But before I explain the different networking layers, I just want to point them out to you in this hex dump. So that purple stuff, oh, great, it's visible. Link layer. That is the most basic layer. And then that blue stuff at the top represents the internet layer. And then the transport layer is the bytes in green. And then the rest of it's application layer. So most of this, thankfully, right, that's what you want. You want very little extraneous information. Most of the meat should be your application layer. But the rest of the stuff at the top is really just the overhead associated with using the internet. So, but the red stuff is actually important. And it's incredible how so few bytes at the top of that packet make it so that your information can travel through dozens, if not hundreds, of famously reliable internet routers spanning the globe. Let's talk about the first one, the link layer. I swear it'll be fun. OK, so the simplest possible configuration for networking. You have 2 computers, OK? Bear with me. Listen, if the internet only consisted of 2 well-behaved computers, you don't really need these layers at all. So we'll start by making this a little bit more complicated. Let's introduce an array of computers on the same line. There can be quite a few computers sharing this one network connection, which in this configuration we would call a shared bus. But let's say I didn't want any of these connections to be shared, but I still wanted every computer to talk to each other, right? If I have n computers, I would need like n squared connections between each of them, right? So at some point, we have to share a bus here, right? If I have like 100 computers, then I need 10,000 connections between each pair, right, to fully wire the internet. So at some point, for the internet to scale, we got to share some wires. So what problems can occur when sharing a connection like this? Well, for starters, everyone can hear everything all the time. Any packet sent on this line, all the computers see it. In addition, if a packet comes in on this line and each computer receives it, how are they supposed to know which one they're supposed to be listening to? That's basically the question that the link layer solves, right? The disambiguation of traffic on this line. So let's go back to our motivating example. Take a look at the original 14 bytes that make up the link layer. And let's focus instead, we'll reorganize these into 2 6-byte fields. And and the protocol one at the end. Each of these have a specific meaning. The first represents the MAC address of the destination computer. The second is the MAC address of the sending computer. And the third is a keyword that represents the IPv4 protocol. 0800 just happens to be indicating to the destination that this packet contains IPv4 traffic. That's all it means. And that's it. These 3 fields make up the entire link layer. And they call this Media Access Control Protocol, and is by far the most common type of link layer traffic you will encounter. Does anyone know any other link layer protocols? Can you name one? Matei.
No.
Coward.
There was the ring one, the ring share buffer one, but I forgot what its name was.
I'm just thinking ARP.
Oh, you mean other protocol?
Yeah, like a different one, other than this one, yeah. So ARP is basically a way to communicate to all the computers. It's a separate protocol, but all it does is it communicates who has what MAC address. That's it. So it's not hugely important. I'm not going to go into it. But if you were to pull up this packet in Wireshark, this is literally what it would tell you about this layer. I just took a screenshot. It's the same packet. So you can kind of see it. I don't really like the way they display information in Wireshark. That's why I hate it. But if you were to stare at this long enough, you might get it. I don't know. It's kind of obtuse. So that's why I don't like networking. I say teaching a networking presentation. Let's go back to our motivating example. How do these 3 link layer fields solve the original problem? Well, for starters, each of these have their own address, right? It's just numbers. It uniquely identifies it. When a MAC protocol packet comes in, right, that packet is labeled with the address that should receive it, meaning that only the computer that matches it will accept the packet and the rest will ignore it. Problem solved. Done. But question, how does the computer receiving the packet know how to respond? Yes, Matei. Oh, that's big-brained. True. That packet does contain the source address, so you can just put the source address in the destination and send out your response, whatever it is. All right, congrats. You just survived the link layer. You know what comes next? Yeah, that's right. Just kidding. Psych, it's the physical layer. I didn't talk about this earlier. There's a secret layer I didn't talk about, right? This is the one that the computer science professors don't want you to know about, because then you'll become computer engineering. So the reason why I'm mentioning this is because the data from the physical layer doesn't even show up in Wireshark. And why would it, right? The operating system just hides all that. Your hardware even can sometimes just hide that. The hardware of your computer abstracts away like having to deal with like twisted pair Ethernet cables versus fiber optics versus Wi-Fi. It doesn't worry about that. I just want to impress upon you very quickly what it might look like, what additional hidden signals are in every packet you send that have to go over a literal wire. This wire, say an Ethernet cable, is only capable of oscillating its voltage between high and low, 0 and 1, right? Let's say we send a fully formed 4-layer packet as 1s and 0s across the line. The secret information is that in addition to the stream of 1s and 0s that make up your packet, every Ethernet frame will be preceded by this exact sequence of 1s and 0s that I've written in hex. That's why it looks like A. And followed by this sequence, which I've also written in hex, is, it depends on the packet. Basically, that first chunk there, let's see, I could probably, yeah, so that's the sync word at the beginning there. It's just an alternating 0, 1, 0, 1, 0, 1, 0, 1. And at the very, very end, it's 1, 1 instead of 0, 1. That's why that last character there is a B right before the packet. So that signals to the hardware, you know, the sync word helps keeps the clocks of the individual like Ethernet hardware like synced up, and then they actually read that stream as a packet after the sync word and feed it to your computer. It literally just that signal. It's very easy for a piece of hardware to read that signal and synchronize based off of it. That is a CRC32. It's just a checksum. So those 4 bytes right there that aren't zeros. And then you have something called the interpacket gap. You have to send a certain amount of zeros. I think the minimum is like 12 bytes of zeros, it looks like, is how many at a minimum. It could be more between the next packet, but that just gives it some space. And you know, that wraps all the way around to the next packet. So eventually, you get the sync word again and another packet. And that's literally how, like down to the voltage level, that packets are sent across like a wire, for example. And that's all I'm going to talk about for the physical layer, because you know, there's no need to, God, I'm not going to talk about Wi-Fi. So let's transition to a real layer like internet. The internet layer, I bet you've never heard of the internet before. We've already figured out how to get computers on the same network to talk to each other. Unfortunately, we can't connect this wire to every computer on the planet. It's not big enough. So we can think of that as its own isolated local network, and other people are going to set up their own isolated local networks. The question then becomes, how do I connect my network to your network and have all of our computers be able to talk to each other? The internet. Let's go back to our original packet. Let's take a look at the original 14 bytes that make up, I think it's a little more than 14. Anyways, is it 20? All right, 20 bytes that make up the internet layer. There's a typo in my notes. I knew that wasn't right. There's actually quite a bit more information in this than there is in the link layer. And I can't fit it all on one slide and talk about it reasonably. So let's just, we'll go through these quickly, but one at a time. Let's do this. First byte, 45. Anyone guess what the 4 means? That's literally all it means. It just means you're using Internet Protocol version 4. The 5, the second digit, indicates how many bytes long the header is, because it could change. It could be different, right? The 5 means 20, obviously. You multiply it by 4. You can only increase the size of the IPv4 packet in increments of 4. So that 5 happens to mean 4. The IPv4 header fields are variable length, and they can contain what's known as option flags, but no one uses that. Differentiated services field. Yeah, there's exactly 2 things you need to know about it. It's sometimes used for real-time data streaming, such as voice over IP, and 99% of the time it doesn't matter. Next byte is the total length of the packet. This includes the header and the payload. It happens to be 377 bytes long in this one. If the size can be 2 bytes, how big is the largest possible IPv4 packet? This is 65 something, right? I know it's 65,000. It's 65,536 bytes. It's just the biggest number that could be held with that much space. That's all. That'll come up later, surprisingly. Identification. The next 2 bytes are a unique identifier for that packet. Why do I need to be able to ID my packets? This has to do with IPv4 fragmentation. We just mentioned that packets can be up to 65,535 bytes long. That'll come up a 3rd time, just you wait. However, the truth is that routers on the internet aren't required to be able to handle any packets longer than 576 bytes, I think. What many routers do is break your huge packet into the largest packets that they can possibly handle and give each fragment the same ID number. So when they get to the destination, they just put them all together. They pretend they were just one big packet. Flags. This is like a bitmap. Each 1 and 0 means something. I'm not going to get into it, but the 4 means that the sender of this packet does not want the packet to be fragmented. If at any point the packet hits a router that needs to fragment it to send it along, the router will drop the packet instead. That's all that means. The zeros after the 4 is called the fragmentation offset. They indicate roughly what order to put the packets back together in if they are fragmented. And if those last 3 numbers are not a 0, you are looking at a fragment of an IPv4 packet. That's what that means. Time to live. Very imposing. 64 in this one. The time to live is a mechanism to prevent a packet with an unreachable destination from being routed endlessly forever on the internet. Something that did in fact happen in early versions of the internet, so they had to fix it. Vintsurf specifically had to fix that. Anytime a router receives an IPv4 packet, it will decrement this number by 1 and send it along its way. Once it reaches 0, the packet is brutally slaughtered where it lies. And the router that killed it will send an ICMP, which is another protocol, packet back to the original host, letting them know where the packet died. This is a real fun fact. Anyone here ever used traceroute before? Use traceroute? This is how it works under the hood. All traceroute does is it sends the same IPv4 packet over and over and over again, starting with a time to live of 1, then with a time to live of 2, and incrementing so on and so forth. And each router along the way that kills the packet is going to send an ICMP packet back to the host telling them where it died. That's how traceroute works. It's awesome. Yes. So with only 1 byte, though, the maximum time to live is 256, which means there is a hard limit on how big the internet can get. It is impossible to send a packet through more than 256 routers. I think it's a fun fact. I'm sure at some day in the future it will not be a fun fact, but for now it's a fun fact. Protocol. All the 6 means is that it's TCP. If it was UDP, it would be 17. If it was ICMP, it would be 1. They're just assigned random numbers, really. Header checksum. The next 2 bytes are a header checksum. That's all I wrote. Source address. Oh, you know, I'll add one thing. So what happens if the checksum is wrong? You just drop the packet. You just don't process it, because clearly something went wrong. That's all that means. Source address. The next 4 bytes are the IPv4 address of the sender, and the last 4 are the IPv4 address of the destination. Why do I need a unique address when I already have a MAC address? Well, the problem is that MAC identifies you only on a local network. In fact, they are not necessarily unique. You can change your computer's MAC address to whatever you want, especially helpful when UCSD Wi-Fi bans you. Every iPhone in the world has actually had the same MAC address for 6 years now. They come out of the factory like that. It's awesome. So yeah, the MAC address is not unique. The IP address, on the other hand, is globally unique, theoretically. We will talk about exactly how that uniqueness is enforced momentarily. And this is what it would look like if you pulled it up in Wireshark. This is what it shows you. It really breaks down the flags for you, so you can kind of see more of that information. But other than that, there's not much more here. IP address spoofing. It's a thing. You can just set, if you have full control of your computer, you can set your IP address to whatever you want. But the truth is, most routers are going to filter out traffic that doesn't make sense. Most routers understand what the structure of the internet is. If you have an IP address that is not likely coming from a certain destination, it will probably filter it out. If it's used to seeing it coming from that port, but it comes in from this port one day, it's going to say, oh, that's weird. And then that's why generally it's difficult to spoof your IP address. However, the closer you are to the person to whom you want to spoof your IP address, the more likely it is that it'll actually get delivered, because there's less routers to filter, basically, just between you and them. So if you're on the same local network, you might get away with it. If you're 1 hop, 2 hops away, you might get away with it. It just depends. But we'll talk more about what goes into that later. Yes, the computer pointing at the other computer. So how does layer 1 and layer 2 fit together? How does IPv4 enable inter-network communication? Let's go back to our motivating example. The only difference now is that these computers are on different networks and must use internet routers to communicate. Each device here has a MAC address, and the 2 computers have also been assigned IPv4 addresses. Let's say the left computer is getting ready to send a packet. In the internet layer of the packet, we note the source IP. We note the destination computer's IP. And in the link layer, we have to note our own MAC address, but we don't know the MAC address of the eventual destination. So we just address the packet to our router. That's its job, right, to route it. So it'll figure it out. No big deal. So we send it along. There it goes, traveling through the internet to our router. Our router has the packet. Before it sends it out, it's going to leave the internet layer stuff as is, but change the source MAC address to itself, and it's going to send it away. There it goes. Poof. And it set the destination to the next router in the line. The next router does the exact same thing, changing the link layer information while keeping the internet layer information constant. And then finally, the packet arrives at its final destination. To return the message to the sending computer, you can just imagine the same process playing out in reverse, so I won't show it, because I spent way too much time on these animations. Now, one thing this example abstracts away is the fact that each of these routers is not just connected to one computer. Each router might be responsible for several computers at a time and needs to know about the MAC and IP addresses of all of them. Routers and all computers do this via routing tables, which is to say personal computer routing tables usually only contain one piece of information. Send everything to the outgoing gateway, the router that you belong to, essentially. The computer on the right is also configured to send outgoing packets to its router. But perhaps fittingly, routers are a little bit more complicated. So our router knows our IP address, and it has it stored in its routing table. But how does the other router know to send packets through our router to get to us. Well, the other router doesn't know us specifically, but it does know that our router serves a block of IP addresses that all start with the same prefix. So by storing information about blocks of IP addresses and where to send them, routers don't have to store all 4 billion IP addresses in their routing tables. And this relationship exists in the other direction as well. The rightmost router knows about the rightmost computer, but the left router only knows about blocks of addresses and sends everything in that block to the right router. Using this CIDR is what they call it, CIDR block structure. IP addresses are allocated in a hierarchical fashion across the entire internet. At the top, you have the king router, the Internet Assigned Numbers Authority, which also oversees the root DNS servers, if you know what those are. The IANA, it's hard to say, splits up the IPv4 address space into blocks and assigns them to 5 regional internet registries, one for each major continent. There's one for Africa, there's one for North America. You get it. They literally just take the whole internet and split it up into 5 bricks. Then each regional internet registry further divides that, and then you've got local internet registries, which then generally sell address space to internet service providers, which then sell your house a single IP address and internet connection. So this may be how IP addresses are delegated, but it doesn't translate to how packets are actually transmitted. Because after all, if I'm on the leftmost computer, to send a packet all the way to the rightmost computer would require visiting almost every node in this tree. That top router at the very top of the pyramid in particular is going to see like 90% of all internet traffic just to route it, right? So in reality, the internet is not structured like a tree or a pyramid. It's a graph, right? So each of these ISPs kind of get together and agree to peer with each other and create redundant connections. So now you've got this really complicated graph of interlocking networks that kind of make up the internet. This way, there are usually multiple ways to route internet traffics, and congestion and collisions can be kept to a minimum. But now, the internet is officially complicated, because figuring out which paths to route traffic down is actually incredibly difficult, almost unsolvable, and the ISPs have to solve that problem. That's their job, and they're pretty bad at it. To do so, ISP routers communicate using a protocol called Border Gateway Protocol. If I wanted to describe to you how BGP works, we would need another 6 presentations, and I don't get paid for this shit, so that's not happening. But perhaps some of you have heard of high-profile hacks that have taken place using BGP. They're incredibly difficult to execute because you essentially have to be or take over an internet service provider. But for example, there have been some suspicious instances of ISPs associated with authoritarian governments using BGP to erroneously redirect traffic associated with certain websites for short periods of time. They can only get away with it for short periods of time before all the other ISPs gang up on them and say, no, you're wrong. So, for example, Iran once claimed ownership of an IP space used by Telegram for a few hours. And China does this a lot too. China and Russia have also done this on multiple occasions. But unfortunately, because these are nation states, we don't really know what was done with the redirected traffic. We can speculate and say they were trying to spy on journalists and all this other stuff, but at the end of the day, we'll literally never know. However, there is one very interesting case in which we know everything because it is not a nation state. There is a very interesting case in February of this year where there was a BGP attack carried out on a South Korean crypto exchange. This was fun. So literally, these hackers wanted to steal crypto from a Bitcoin exchange in South Korea. So instead of hacking the Bitcoin exchange, they built an ISP and then just redirected all the traffic from the ISP to them, and then they just stole people's sessions and then stole their Bitcoin. It was hilarious. You can read about it. You could probably find it if you Google for it, but we know almost everything about the attack, and it's very interesting. And here in the year 2022, we still have to worry about what people are doing with BGP. But thankfully, we don't have to worry about it today. That concludes the internet layer. Y'all are masters of the internet now. Let's move on to the dreaded transport layer. Yeah. What? There's more problems to solve at this point, right? That's right, folks. We may have built the internet, but here's all the stuff we have to do to make sure it doesn't suck. How does internet traffic ever get reliably delivered? In order and without loss and errors? Well, there's actually 3 problems here. So the first problem I like to call reliability. Actually, everyone calls it that. This is our anatomically correct model of the internet, the entire internet. The first problem we need to solve is one of reliability. Let's just focus on these 2 computers for now. They're trying to talk to each other, okay? We already have the internet. It exists. I want to send an internet packet to my friend next door, which as far as UCSD Wi-Fi is concerned, might as well be on the other side of the planet. Off goes the message containing my secret. Let's see here. Oh, did it? Where'd it go? Oh, it just died instantly? It didn't work. That's crazy. What's going on, UCSD? Well, in the real world, packets can get lost in transmission, collide with other signals on an Ethernet line, get blasted by cosmic rays from outer space. The technical term for this is shit happens. And thanks to this, my message goes unreceived. The second problem we need to solve is packet order. So let's say my love letter is so lengthy that it cannot be contained in a mere single packet, of which the maximum length is 65,535. I must transmit 3 packets, and I will send them in order. Unfortunately, even if I send them in the right order, shit happens. So they'll travel across the internet, but when my friend receives my packets, they need a consistent way of figuring out what order to read the packets in, right? I've numbered them here, but in reality, they have no way of distinguishing them. If we had a way to figure out the order, this might also have the side effect of making it easier to figure out if we're missing one. So this is a worthy problem to solve. Lastly, we must address the problem of my favorite SAT word, disambiguation. Up until now, we've been operating on the foolish assumption that each computer is running application. One application, I should say. But we know this isn't true. There can be a terrifying number of processes running on a single computer, especially if you have Chrome open. Each process may have its own networking activity, and to make matters more confusing, all this traffic is almost always going to come in on one damn wire. The operating system needs to have a way of figuring out which packets should go to which applications running on the computer. After all, we don't really want TikTok to be able to see our online banking traffic. To answer these questions, we must consult our old friend, the hex dump. This time, we are emotionally invested in the green bytes. Let's bring our contestants up to the stage. These 20 bytes make up a protocol called Transmission Control Protocol, which we will call TCP because it's less difficult. Like last time, we will go over each piece one at a time, but it will be quick. Starting with the first 2 bytes, we have the source port. What is this used for? Well, this is used to indicate which application on the originating computer is sending the packet, right? In this case, it happens to be 45,878, which is an ephemeral port, but we'll talk about that later. You can probably guess what the next 2 bytes are. Correct, destination port, which in this case is port 3000. This says which application on the receiving computer I am trying to talk to. You can think of it like this. The IP address is used to indicate which computer in the world you want to talk to, and the port indicates which application on that computer you want to talk to. It's like the first and second line of an address you write in an envelope, respectively. So together, the source port and the destination port solve the disambiguation problem, right? 4 bytes in, and we've already solved one of our problems. That's great. Let's see what's next. Oh, next 4 bytes make up the sequence number. You could probably guess from the name. Every time we send a packet in the TCP stream, we increment this sequence number so that the receiver's operating system can put them back together in the correct order before giving it to the application. This solves the order problem, and the next 4 bytes are very closely related. And they make up the acknowledgement number. This This is a little bit harder. Both computers in a TCP conversation have their own sequences, their own numbers, essentially. The acknowledgement number is the last sequence number that I received. I'm telling the person that sent me this packet in response, I received your last packet, right? This helps address the reliability issue. Helps. If the acknowledgement numbers don't match the packets that I've sent, I know I might need to resend those packets. And the next 2 bytes are a little bit more interesting, pun intended, because it's a bitmap. The first 4 bits represent the header length. 5, once again, means 20 in this case. And then you'll notice that the last 12 bits represent various flags that indicate certain types of TCP packets. Most of them are only relevant for setting up the connection. So when the TCP stream starts between 2 applications, it has to do a bunch of setup, and it has to close the stream and address congestion. That's what the rest of these various flags are for. The first one is the first one in this sequence is the acknowledgement flag, which is just saying that the receiver should look at what you have set as the acknowledgement number. It's important, right? It's updated or something. The second one is the push flag, which just means that the receiving application should process this data immediately with no buffering, and that's typically what web servers do. So, there are others, but let's just move on. This is a crash course. Let's see here. Next 2 bytes are a value called window size. It has to do with the remaining number of packets the sender has memory for. So if it reaches 0, that's a polite way of telling the destination to shut up for a bit while we process stuff. And then finally, the last 2 bytes are the checksum. This value helps verify the integrity of the message. If the checksum does not match the original, the packet will be thrown away. Same as usual, right? But that will lead to a retransmission in TCP. That's why it is more valuable. Now I said the last 2 bytes, but there's 4 bytes there. You may be wondering, why the extra zeros? What is it for? Well, it's this simple. It's literally just so that the packet aligns on a 32-bit boundary and makes a pretty square. Literally, that's the whole thing. It's easier to make hardware that handles this, is really what it comes down to. Now then, you are looking at the entire TCP header here. It's all on one slide. For the record, this is what Wireshark shows for the same exact TCP packet. Yeah, it's kind of gross. It's all there. It's all the same information. On the topic of security, right? Because I think, is this ACM Cyber? OK. TCP also makes it harder to impersonate traffic because of the random sequence numbers. Even if the traffic appears to be coming from the right IP, if the sequence number doesn't make any sense, it's not going to work. So that's why it's important that the sequence numbers are unguessable. There was a time where they were very predictable, and it led to major security issues. In conjunction with IPv spoofing, you can do a lot of damage. So, moving on from the packet structure, let's talk about how these connections are established. Very quick. It's called the TCP Handshake. It's just a 3-way process. There's a 3-step process. Our hosts, in order to communicate, need to agree on sequence numbers, window sizes, and ports. It does this via the 3-step process known as the TCP Handshake. In this model, there is a server listening for incoming connections on a particular port, and there is a client that initiates the connection. The client starts by sending a TCP packet to the desired port with the SYN flag set, which just stands for synchronize. In this SYN packet, we need to provide an initial sequence number, but we don't know the acknowledgement number. We set that to 0. And we also have to indicate which port it's destined for, and as well as what port the server should respond to. And again, that port is ephemeral. So when you initiate the connection, your OS generates that for you and just reserves it. So any traffic coming back, it knows to associate to the app that opened the connection. Once we're all set, we send it. There it goes. Once we receive the SYN packet, the server must do a few things. First, we must include the SYN ACK flags, and we have to swap the source and destination ports. If you missed it, you also notice that the sequence number has been moved into the acknowledgement numbers spot, right? The server must create its own sequence number to send back, but it also needs to increment your acknowledgement number, indicating that the next sequence should be sent. Now the server's response is looking good. We send it on its way, comes back, there we are. Once the client gets its response, it needs to finish the handshake in a very similar way. We swap the ports, we swap the numbers, and we only use the ACK flag. We're just acknowledging the last step of the process. Oh, and don't forget to increment the acknowledgement. And we throw that last packet right back, and the handshake is complete. 3 steps, done. So the benefit of this whole 3-step process is that now our computers are synced up. We agree on this information. Data can flow freely both ways. Packets arrive in order without errors and disambiguated. By the way, once these computers are finished talking to each other, the aptly named fin packet will be sent to close the connection. One last thing. We can't forget that this whole conversation is happening over the internet. There are devices such as routers between the client and the server that don't even operate on the 3rd layer, right? The transport layer is a bridge connecting individual applications on these computers, while the internet layer is what all 3 of these use to communicate, while the link layer is what supports that, and the physical layer binds together everything above that. The abstract data flow is layer 3 at the top, right? We don't have to think about all the stuff that happens below. But the actual data flow goes like this, you know? It goes up and down, and all of them work together to enable this deceptively simple data flow at the top. And I just graphed all of 123. And that concludes my presentation on the transport layer. It's now time for the dreaded, massive, confusing, multidisciplined application layer. Let's go to the hex dump. So there it is, big, bulky. At this rate, I might not finish my presentation before I graduate. Fortunately, this is going to be the shortest section by far. The red portion in this data is actually just plain text. You can read it with your eyes, unless you need like contacts or something, I don't know. This is plain text. What application layer protocol is being used here? Wow, how'd you know? You can see it on the first line that we're using HTTP in order to get a web page. But in order to understand the rest of it, we're going to need to memorize the entire HTTP spec in its entirety. Is everybody ready? Yeah. All right, we're going to read the original RFC for the World Wide Web. Go. No. Any comments? What was your favorite part? Okay, good. Done. We finished the application layer. Now, it is time for... I finished explaining how the entire internet works, and now I have to show for you a 30-step demo. Woo! I had to print it out and shit. All right. Good Lord. Okay, so this was originally going to be collaborative, but then it was so hard I could barely do it. So I'm just going to try to survive here. So I want to demonstrate to you with a motivating example, an unsolved web challenge from UIUCTF, the last competition they had last year. And this kicked my butt. I was so frustrated after doing this challenge because I am the web hacking master, but I didn't get it. No one solved it, including me, and I'm special. So I was so angry, I swore to myself I would learn everything there is to know about networking. So I signed up to do a networking presentation and had to read every Wikipedia page on networking in order to give this presentation. So it worked. Now, let's go ahead and do the challenge. Woo! All right. We'll see if I survive. I'm going to go ahead and make my displays duplicated